which is totally fine and even normal given our circumstances. So I just wanted to make this little video so that everyone feels like they've had everything explained to them at least one extra time, and hopefully that helps. If you need to hear this in Spanish, YouTube auto creates subtitles. Some of them are in Spanish. All right, so for an overview, we're going to start from the beginning, talk about atomic structure. We're going to talk about neutrons in mass, electrons in charge, electron orbitals, what is a valence and what isn't. Then we're going to talk about why atoms become ions. Then we're going to talk about our CER, our claim evidence reasoning that we did earlier this week. Then we're going to talk about the periodic table simulation, which was homework a few classes ago. And then the flame test lab, which is technically your homework for this Thursday, Friday, October 1st and 2nd. Let's jump into it, shall we? So, atomic structure, you guys know this. There's protons, there's neutrons, there's electrons. Protons and neutrons have mass, electrons do not. Protons have a positive one charge, electrons have a negative one charge. The protons and neutrons hang out together in something called the nucleus, and electrons buzz around the outside. All right, nothing crazy or weird there. I found that we have a lot of issues, though, dealing with a number of neutrons and mass. So the number of protons in all atoms of the same element will always be the same. All carbons have 6 protons, but not all carbons have 6 neutrons. Some have 6 neutrons, some have 7 neutrons. This changes their mass. The mass of an atom is the number of protons plus the number of neutrons. So if you got 6 protons, 6 neutrons, mass of 12. 6 protons, 7 neutrons, mass of 13. If you have a mass of 14 and 6 protons, okay, I can find the number of neutrons by subtracting those. Mass of 14 minus 6 protons is going to give me 8 neutrons. We have similar issues with electrons in charge. So electrons are negative, protons are positive. The charge is when you do protons minus electrons. Minus because they're negative. So if you have 8 protons and 8 electrons, you have a charge of 0. If you have 8 protons and 10 electrons, 8 minus 10 equals -2 charge. Which means I could also do this the other way around. If I know the charge is -2, and I know I have 8 protons, I could do 8 minus -2, which is the same thing as 8 plus 2, to get 10. There's another way of thinking about it, though. If you have the same number of positives and negatives, protons and electrons, your charge is 0. If you do not have the same number, you have a charge. In this case, on the bottom, I have 2 extra electrons, which means my charge is 2. And since electrons are negative, it's a charge of -2. All right, now these electrons hang out in orbitals. The very smallest orbital only has room for 2 electrons in it. If you look at lithium, for instance, it has 3 electrons total, only 2 in the first shell. It can't fit 3 in the first shell. Luckily, there are more orbitals. All the other orbitals, at least the ones we're going to work with, have 8 spots for electrons. So if you look at sodium, there are 2 electrons in the first orbital. There are 8 in the second orbital. And then the last electron has to go in the third orbital. So you start by filling up orbital 1 with 2. Then you fill up orbital 2 with 8 total. Then you start filling up orbital 3 with 8. All right, now we got some names for these things. Whichever orbital has electrons in it and is the biggest, we call the valence shell. So hydrogen only has 1 orbital, so that 1, the first one, is the valence shell. Lithium has 2 orbitals. The biggest one, orbital 2, is the valence shell. Sodium has 3 orbitals. So the biggest one, the third orbital, is the valence shell. All right, now valence electrons are how many electrons are in that shell. So sodium has one valence electron, because although there are 11 electrons, there's only one in the biggest shell. Magnesium has two, because it has two in its biggest shell. Aluminum has three, because it has three in its biggest shell, and so on. So what we're talking about here, of course, are neutral atoms, not when they're ions. We're talking about a neutral sodium, a neutral magnesium, a neutral aluminum, which means they have the same number of protons and electrons. But we know that sometimes they become ions. The reason they become ions is because atoms don't want their valence shell, the biggest orbital, they don't want it to be half filled or partially filled or almost fully filled. They either want it empty or completely filled. Let's look at lithium. Lithium has 3 electrons, 1 valence electron. It's going to lose that 1 valence electron, which means now the valence shell is the first orbital because it's now the biggest one with electrons in it. And that one is already filled. So by losing those extra electrons on the outside, lithium got to stable. It got to happy. It got to a full valence shell. Let's look at oxygen. Oxygen has 2 electrons in the first orbital, 6 in the second orbital. It has 6 valence electrons. It wants either 8 or 0. It's going to be lazy. Losing 6 is a lot harder than finding 2 more. So it's going to find 2 more, plug them into its empty spots. And now it has 8 valence electrons. So it's happy. It's stable. The valence shell is full. Of course, this means that I now have 2 extra electrons. So I now have a -2 charge. All right, we've talked about this, as stated before, a bunch of times. Why is sodium so reactive? You throw sodium in water, it explodes. Magnesium in water doesn't explode. Aluminum in water doesn't explode. Why does sodium explode in water? It's because sodium only has 1 valence electron. It's so close to being stable that it loses that electron real easy. It's easy for it to become an ion. It is easy for it to become stable. So it does, very easily. We call that being reactive. Aluminum, on the other hand, it has to do a lot more work. It has to lose 3 electrons, not 1 electron, 3 electrons. So it's less reactive because it has to do all 3 at the same time. It can't lose 1 here and 1 there and 1 there. It has to lose all 3 at the same time. And that's harder. So it doesn't do it as often. Because again, atoms, be lazy. Now, we then used this model to try to predict between nitrogen, oxygen, and fluorine what would be most reactive. Well, nitrogen, if you look at the Bohr diagram, it needs 3 more. Oxygen needs 2 more. Fluorine needs 1 more. So fluorine is the closest to being stable. So it is the most reactive because it has to do the least amount of work. Nitrogen has to do 3 times the amount of work. So it is not as reactive. All right. Jumping now to the homework from a few nights ago. If you have not done the simulation, you really need to do it. You need to get a picture of it to put in your report to get credit for it. But here are the conclusion. So jumping to the conclusion. What you should find is that as you go down a column, the atoms get bigger, but as you go across a row, the atoms get smaller. All right. Why? And I just need you to, think of a reason why. It doesn't have to be correct. But your first hint is that it's not the number of protons. As you go down, you get more protons and you get bigger. But as you go across, you get more protons, but get smaller. So it can't be protons. Think about, hint 2, your Bohr diagrams. What else is changing that might explain why they get bigger as you go down? Don't worry about smaller as you get across too much. Focus on bigger as you go down. What else is different that could cause the atoms to be getting bigger? All right, and then your homework for Thursday, Friday. was our next lab. So again, there's a video, you watch the video, you record what happens, you answer the analysis questions, not that big a deal. The thing you're going to hand in is called the Flame Test Lab Report. However, the actual lab video and a hint about doing the conclusion can be found under Flame Test Materials. The big question for this lab, the thing that we want to figure out is, why do things burn different colors? Think about fireworks. Why are some fireworks blue, some green, some red, some white? That's because they're burning something that burns that color. Why do things burn different colors? And what things burn what colors? That is what this lab is about. I mean, it's a good one, so once we get back into the classroom, chances are we'll do this one again in person because it's awesome. All right, that brings me to the end of this general overview. Hopefully that cleared up any small misconceptions, any bigger issues that you still have with the material. Please email me, please, and I will do what I can to help. All right, thank you very much. Have a good day.